Morning. Hope you all had a good weekend. So this week, you're going to do lab number 6. Make sure you get your pre-lab done before your lab section starts. It is RC circuits you're going to be looking at, but this time you'll look at the electrical version of RC circuits. And then that's pretty much the only announcement. We have our usual homework due on Friday, and then we have quiz number 2 coming up next week on Wednesday. Okay, so what I want to do today is I want to basically build the strategies that we can use to analyze some simple circuits. And the simple circuits that we're going to analyze, which will basically be what we look at for the rest of 121, I guess, for the circuits part of it, is we'll look at circuits that involve just batteries and resistors. Okay, and the tools that we're going to use to analyze these circuits are the Kirchhoff rules. The first one was the loop rule, where we keep track of all the changes in voltages around a closed loop in a circuit. And if we add up all those voltage changes, they have to sum to 0. That was a conservation of energy requirement. The second rule, which we developed more recently, was the junction rule. And it says that if we have a junction in a circuit where we have a bunch of wires like splintering off, and like a fork in the road, then what we require is that if we sum all of the currents going into that junction, it would have to be equal to the sum of all of the current headed out of that junction. And those are the 2 fundamental rules that will apply. One thing that we'll have to keep in mind is that we're going to have to analyze voltage changes across resistors, and whether the voltage change is positive or negative will depend on the direction that we cross that resistor. So the magnitude will always be IR. It will be minus IR if we cross a resistor in the direction of the current, and it will be plus IR if we cross the resistor in a direction opposite of the current. Okay, and so those two Kirchhoff rules and that one rule of thumb for voltage changes across the resistor is everything we need to analyze circuits that are going to look something like this. So here's an example of a circuit that involves only batteries and resistors. There are 3 resistors and 3 batteries in this case. This is a circuit that has a couple of branches, right? It has like a kind of an outer loop, and then it has a branch that goes down the middle. And what we're going to try to do is develop some strategies for tackling these problems in a systematic way. So usually in this type of problem, what we're going to have is 3 unknowns. So typically what might happen is you might be given the voltages of the batteries, and you might be given the values of the resistors. And the question would be, what are the different currents in this circuit? So that's a pretty standard question. Or you might be given some values of some of the currents, and you said, find the voltages of the batteries or something like that. But there's going to be some unknowns, and we're going to have to set up a system of equations to solve for those unknowns. Okay, so typically in a circuit like this, we will have some unknowns to solve for. Those unknowns could be currents or battery voltages or resistor values. Whatever the unknowns are, what we're going to have to do is set up that system of equations to solve for them. So we need to set up a system of n equations to solve for our n unknowns. Okay, and so let's just be specific and let's do an example. So example in the circuit above, whoops. In the circuit above, find the current in each branch or each resistor would be an equivalent. Each branch of the circuit, or equivalently, the current in each resistor. Okay, so we're going to break this down into a series of steps that if we follow, we can apply to every type of circuit like this, any kind of circuit that involves some combination of resistors and currents. And this strategy will always work if we follow it correctly. So, step one. We're going to assign a current to each branch of the circuit. So what I mean by assigning a current is we're going to label a current. So we'll have like an I1, an I2, and an I3. And we'll specify a direction for each current. So we're going to label the currents and pick a direction. So it's going to turn out that the direction that we choose is not going to matter as long as we're consistent through the analysis. Once we assign a direction, we keep the current in that direction throughout the rest of the analysis. What we might find is at the end of the problem, we calculate a value for the current. If it comes out to be negative, that just means we picked the wrong direction. Everything else in the problem will have been solved correctly. We just have to notice that if I solve for a current and find that it's negative, it just means that the actual direction is opposite of what I picked. Okay, so if at the end of the problem, we calculate a negative value for a current, it just means that we chose the wrong direction. So all other calculated quantities will be correct. Okay, so that means we don't have to we don't have to redo any calculations. We just have to know that we happen to choose the wrong direction for our current. Okay, so before moving on to the other steps, let's just complete that first step. So when I look at this circuit, I would say it's a 3-branch circuit. There is a branch that is on the left-hand side. It involves the battery V1 and R1. And then there's a junction at the top and the bottom. So there's one junction, we'll label it, say, junction 1 at the top, and then there's junction 2 at the bottom. Okay, so that first branch goes from junction 1 to junction 2 and involves V1 and R1. And then there's another branch of the circuit that goes from R2 and V2 it's also between the same two junctions. And then the third branch is on the right-hand side. It involves V3 and R3. And so we can call these branches, I don't know, branch 1, branch 2, and branch 3. And so the first step in our analysis is to assign currents to each branch and give a direction and a label. So we can do that. I'll say that the current in that first branch, we'll call it I1. And I just picked a direction. I happen to pick from J2 towards J1, or like an upwards current through that first battery. And then I'll pick another current for the next branch. And so there it is. We'll call this one I2. I've also just chosen upwards for no particular reason. I just have to make a choice. And then finally, we have our third branch, and we'll assign a current I3 in that third branch. And this time, we'll make that current go downwards through R3. Doesn't matter, just got to make a choice. Okay, so that's it. That's step 1 is done. So the next step we'll do is we'll identify our unknowns. So step 2 is identify the unknowns. So for the problem we're doing right now, let's assume that we were given, I didn't write down any values, but let's assume that we know the voltages of the batteries and we know the values of the resistors, and what we want to find is the currents, I1 and I2, I3. So in this example, so assume battery voltages and the resistor values are known. The unknowns are I1, I2, and I3. Okay. If we have 3 unknowns, like we do in this problem, what it's going to require for us to solve the problem is that we have to construct a system of 3 independent equations that all involve the unknowns so that we can solve them. When I say independent equations, what that means is I can't take 2 of the equations and then use them to construct the third one. If that was the case, then that third equation would be not independent of the first 2. Okay, so to solve for our 3 unknowns, we need to construct a system of 3 independent equations involving the 3 unknowns. Okay, good. So there is our circuit. We've labeled our current. We've identified the unknowns as the values of I1, I2, and I3. And so the next step will be to start building that system of equations. And to build the system of equations, what we're going to do is we're going to make use of the Kirchhoff rules. I'm actually going to start with the junction rule. And so we go back and we look at our circuit, and we have 2 junctions, J1 and J2. So we'll make our third step. Step 3 is let's apply the junction rule to start building our system of equations. Okay, so let's take the junction J1, and we're going to require that the current in equals the current out. Okay, so we go look at J1, and if I look at the current I1, it's headed towards J1, so that contributes to the current in. If I look at I2, it's also going up towards that junction. That's also contributing to the current I in. And then finally, we've got I3. It's flowing away from the junction J1, and so that's part of I out. So what we would have from our junction rule for J1 is the current in, I1 plus I2, must be equal to the current out, which is I3. So for junction 1, we have I1 plus I2 combined to give the current into the junction, and that has to be equal to I3, which is the current leaving the junction. Okay, and so that's one of our equations. And so I'm gonna call this equation something. We'll call this, let's say A. All right, now, of course, we have a second junction. And so let's take a look at what happens if we examine J2. So we go back down, J2. So the current I1 is flowing away from J2, as is I2. So I1 and I2 combine to make the I out for the second junction. And then I3 is coming down on the right and then takes the corner and heads towards J2. And so that's the current in. So for J2, we would say the current in is going to be I3, and that has to be equal to the current out, which is I1 and I2. So this is I in. This is I out. And if you look at that, that's the exact same condition on the currents that we got from looking at the junction J1. And so this is the same result from J1. And so there's no new information. And that's always going to be the case in, you know, all the vast majority of the types of problems that we'll solve in physics 121 of this type will be these 3-branch circuits that have 2 junctions. And it's always going to be the case that the junction rule applied to each of those junctions will lead to the exact same expression. So you really have to only analyze one of them. Okay, so our junction rule gives us one of our required 3 equations. The second equation is not independent of the first one because they're exactly the same. Okay, so that's step 3. Let's do step 4. Is we're going to use the loop rule to find the other 2 required equations. Okay, and this is the part where we're most likely to make mistakes. And the only reason that you may make a mistake here is if you don't properly apply the rule of thumb for tracking the voltages across a resistor. So we're going to have to cross resistors. We have like an R1, an R2, and an R3. So there's 3 of them. And we're always going to have to look, are we crossing the resistor in the direction of the current? In which case the voltage change will be minus I times R. Or are we crossing the resistor opposite the direction of the current? In which case the voltage change will be plus I times R. That's the only thing we have to worry about. Okay. So if we go look at our example, how many loops do we have in this 3-branch circuit? How many loops can people see here? 3, that's exactly right. We have a loop on the left-hand side, which involves V1, R1, R2, and V2. We have a loop on the right-hand side, which involves V2, R2, V3, and R3. And then there's an outside loop that skips over the middle branch and involves V1, R1, V3, and R3. And so we could label those. So we would have loop number 1 would be something like this, the inside loop on the left. Loop number 2 would be something like this, an inside loop on the right. And then loop number 3 would be one that would travel the circumference of the circuit. And so it would look something like this, and we'll call that loop 3. Okay, now we need a system of 3 equations to solve for our 3 unknowns. We have one equation from the junction rule, and we have 3 loops available to us. We can pick any 2 of the 3 loops to use. It really doesn't matter. Okay, so we'll start with loop 1. And let's start in the bottom left corner, and we'll go around clockwise as we've drawn that purple loop. So the first thing we do is we cross the battery V1 from the negative to the positive terminal. So we're going from low to high potential. And so we gain the voltage of V1. Then we're going to cross the resistor R1 in the direction of the current I1. And because we are going in the same direction as the current, we're going to lose a voltage of minus I1 R1. So let's write those down first of all. So let's take loop 1. And so the first thing we did is we crossed the battery V1, and I'm going to put a plus sign because we went from the positive, we went from the negative to the positive, negative to positive terminal. So we went from low potential to high potential. Then we have minus I1 R1, and this is because we go in the direction of I1. Okay, so those are the 2 things that we've done so far. And to finish our loop, we have to come down through the middle branch and go through R2 and then V2. So the first thing we do is we cross R2. Should I use plus I2 R2 or minus I2 R2? Plus, okay? This time, we're going to cross the resistor going down, which is anti-parallel to the upwards current. And when we go in the opposite direction of current, we should gain the voltage. And then we're going to cross V2 from the positive to the negative terminal. So we're going to go from high to low potential. So we're going to lose voltage of minus V2. Okay, so this time, to finish our loop, we would go plus I2 R2. So this is opposite direction of the current I2. And then we go minus V2. And that's because we went from the positive to the negative terminal. And all of these things would have to sum up to give 0. So 0 is equal to all of that stuff. All right, so that's one of our loop equations. Let's just do all of them so that we can get some practice. And it'll also lead to some useful insights, I hope. We'll see. So the second loop. This time, let's start at the junction J2, and then we'll go clockwise. So we start at J2, we cross V2 from negative to positive, so we get plus V2, and then we cross R2 in the same direction as the current I2. So we have minus I2 R2. So it's plus V2 minus I2 R2. So we're going to have plus V2 minus I2 R2. Okay. And then we're going to continue to go clockwise around this internal loop number 2. We'll go from the positive terminal of E3 to the negative terminal. So we're going from high to low potential. We're losing voltage minus V3. And then we go through R3. Is it plus or minus I3 R3? Minus, that's right, because we're going to go in the same direction of the current. And so this time we have minus signs for both terms. Minus I3, minus V3 minus I3 R3. So minus V3 minus I3 R3. Okay, and let's do the last one, just for completeness. Like I said, we only need to do 2. We can pick any 2, it doesn't really matter. We have 2 of them, we could stop here and we could continue to solve our problem. But let's just practice this third loop. All right. The third loop starts the same as the first loop. If we start in the lower left corner, we cross V1, we get plus V1. We cross R1 in the direction of I1, so then we get minus I1 R1. Okay, so plus V1 minus I1 R1. So that should look like the start of the first loop equation, and in fact it is identical. Okay, then to finish our outer loop, we're going to skip over the middle branch, and we do V3 from positive to negative terminal. So we go minus V3 and then minus I3 R3. That should look like the end, the last part of the second loop. So it should be minus V3 minus I3 R3. So minus V3 minus I3 R3. And then I got a mistake here, right? This should be a V3. Okay, good. All right, so we have our 3 loop equations, and what I'm going to claim is that if we were to do something like, let's imagine that we took, so these are, let's just make a summary. So these are our 3 loop equations, and I'm going to claim that there are only 2 independent equations. So that means we should be able to take 2 of the equations and use them to construct the third. So let's consider, let's see, what do we want to do? Let's consider the loop 1 equation minus the loop 2 equation. Sorry, I didn't want to do 2. Okay, yeah, actually, let's do that. Let's do loop 1 plus loop 2 is what I want to try. And if you look at loop 1, the last 2 terms are plus I2 R2 minus V2. And if you look at loop 2, the first 2 terms are plus V2 minus I2 R2. So they're the same, except they have the opposite sign. So let's see, if we did that addition, we would get, so I'll just write out everything. So loop 1 will be plus V1 minus I1 R1 plus I2 R2 minus V2. So this is going to be loop 1. We're going to add to that loop 2, which is V2 minus I2 R2 minus V3 minus I3 R3. So that's adding up the, I guess, the right-hand sides as I've drawn them. And that would have to be equal to the sum of the left-hand sides, which is just 0 plus 0, right? Okay. But then we could see, if we did this addition, I have minus V2 and I have plus V2. Those just cancel. And then I have plus I2 R2 and minus I2 R2. Those ones cancel. And then we just have the remaining terms. So we're going to end up with V1 minus I1 R1 minus V3 minus I3 R3 is equal to 0 plus 0, which is just 0. And that should be exactly what we have for loop 3. So V1 minus, yeah, that's right. So this is exactly equal to the loop 3 equation. Okay, so since we can construct the third equation using the first two, we only have two independent equations. Now, what we did is we used the first two to make the third. We could have done anything. We could have taken the first one and the third one to construct the second one, or we could have taken the second and the third to make the first one. It doesn't matter however you do it, you're always going to come to the conclusion that there's two independent equations which can always be used to make the third one. So for our system of three equations that we're trying to build, one of them is going to be the junction rule. And then two of them are going to be loop rules, and you can use any of the three loops that we worked on as your two independent equations. Okay, so then let's see, let's make this, let's go to step 5. Step 5 is to finalize the system of three equations. We need to use one junction rule, and we need to use two from the loop rule. Okay, and so for this example, for the current example, we're going to have our junction rule led to I1 plus I2 is equal to I3. And we already called that equation A. Did I get that right? I2 plus I3. I1 plus I2 is I3. Yeah, that's right. Okay, and so now we need to use our two of our loop rules. I'm just going to pick the first two. It's just arbitrary. It doesn't really matter. So our second equation will be V1 minus I1 R1. Okay, so it's going to be V1 minus I1 R1. And then what was it? It was plus I2 R2 minus V2. So plus I2 R2 minus V2. And so we'll call this equation B. And then for the third equation, I'm just going to use the second loop equation, which was V2 minus I2 R2. So V2 minus I2 R2. And then I think it was minus V3 minus I3 R3. Yeah. Okay, so minus V3 minus I3 R3. I should say that this has to be equal to 0. So let's keep that in there. Okay, so there's our system of three equations. They involve our three unknowns. Our three unknowns are I1, I2, and I3. And so those currents are featured in all three of the equations. We don't need all three currents in all three equations, but all three currents must appear somewhere in this system of three equations. Okay, so for example, equation B does not involve I3, but it is in the other two, so it's okay. All right, at this point, it's no longer really a physics problem. We've done all the physics, the setup. Now it's just a math problem. Solve the system of three equations for the three unknowns. So step 6 is to actually solve the problem. Step 6 is to solve the system of three equations for the three unknowns. Now it's just a math problem. Okay. And so I think I'd like to try to do that. What I'm going to do is I'm going to assign some values for the V1, V2, V3, and then the R1, R2, R3, so that we can actually solve the problem and find the currents. So what we're going to do is, example, let's take this circuit drawn above, and let's assume the following. So V1 is just going to be V. Maybe if you like, it's a volt or something like that, 1 volt. V2 is going to be equal to 2 times V, maybe it's 2 volts then. And V3 will be 3 times V. And then R1 we'll call R, R2 is going to be 2R, and R3 is going to be R, not 3R, just R. Okay, so the first thing I'll do is I'm going to rewrite our system of three equations after making this substitution. So our system of three equations then will be, the first one doesn't change. I1 plus I2 is equal to I3. So that's still just the same equation A. And let's see, the second equation is going to be V1, which will be V, minus I1 R1. And so that's just going to be minus I1 R. And then we'll have plus I2 R2. R2 is going to be 2R. So we'll get 2 I2 times R. And then we have minus V2. And so that's going to be minus 2V. That has to be equal to 0. And so that's fine. What we can do is we can do some simplification of this equation right away. Now that we have some kind of, we have different expressions for V1 and V2. We have V minus 2V, which is just a minus V. And at the same time, I'm going to just divide by R. So we'll end up with minus V divided by R minus I1 plus 2I2 is equal to 0. And that's now our equation B. Okay, so it's just the same equation B above, where we made those substitutions for the voltages and resistors. And then I just combined V minus 2V to be minus V, and then just divide everything by R. Okay, and we'll do the same thing for the third equation. Let's see, V2 is going to be 2V. So we have 2V, and then we have minus I2 R2. R2 is 2R. So we have minus 2 I2 R. And then we have minus V3, which is minus 3 times V. Minus I3 R3. R3 is just R. So it's minus I3R, and that has to be 0. Okay, good. So we'll do the same thing. We have 2v minus 3v, which is just minus v, and then we'll divide all terms by r. So we end up with a minus v over r. Let's see, we'll get a minus 2i2, and then we have a minus I3, and that has to be equal to 0, and that's going to be our third equation, which I'll label as C. Okay, so now we're ready to start solving this system of equations, and there's no right or wrong way to approach this. What we can do is, basically we have 3 unknowns. The first step that we're going to do is we're going to try to take those 3 equations and eliminate one of the variables, and that will leave us with a system of 2 equations and 2 unknowns, which are easier to solve. So what I'm going to try to do is I'm going to try to eliminate I3. And to do that, we're going to work with the 2 equations that involve I3. So we have equations A and C. So to solve this system, we're going to start by using 2 of the equations to eliminate 1 of the unknowns. Okay, what I'm going to do is I'm going to sub A into C to eliminate I3. Okay, so if I start with equation C, we have minus V over R minus 2I2. I just wrote down the first 2 terms, nothing else. And then we have minus I3. But I'm going to try to get rid of I3, and I'm going to use equation A to do that. I3 is equal to I1 plus I2. And so we have an I1 plus I2. And that has to be equal to 0. Okay, that's not so bad. I have now minus 2I2 minus I2. So we'll end up with a minus 3I2. And then in addition to that, we have a minus I1. So therefore, we could write this as V over R minus I1 minus 3I2. And that's equal to 0. I'm going to call this now equation D. Okay, so now if you look at equations B and D, they are 2 equations in the unknowns I1 and I2. So now that's a system of 2 equations and 2 unknowns. So now equations B and D form a system of 2 equations and 2 unknowns. So we've definitely made some progress. So let's see, what's the best thing we could do? I want to eliminate one of the unknowns from that system of 2 equations. The easiest thing to do in this case is to notice that both equations B and D involve minus I1. And so if I subtract one of the equations from the other, I'll have a minus I1, and then I'll have minus I1, and that will cancel. So what we'll do is, let's take, it doesn't matter, we'll take B minus D to eliminate I1, and then we'll have a single equation in one of our unknowns, and the only unknown remaining will be the I2. And so let's see what happens. Okay, so equation B was minus V over R minus I1 plus 2I2. Okay, so this is equation B, and then we'll go minus equation D. So it's minus V over R minus I1 minus 3I2, and the right-hand sides are both 0, so 0 minus 0 is 0. So this is equation D over here. All right. Now, we're going to get minus I1 minus I1. Those are going to cancel. In fact, we get more cancellation because equation B has a minus V over R. Equation D has a minus V over R, but we're subtracting it, so we get minus V over R. That's a plus V over R, and so we'll get some more cancellation right there. And what we're left with is 2I2 plus 3I2 is equal to 0, or 5I2 is equal to 0. What's I2 have to be? 0, right? The only way the left and right hand sides could be equal is if I2 is 0. We could also just divide by 5, and therefore we get I2 is equal to 0. Once you've solved for one of your unknowns, the rest of the problem will go very quickly, because now what I can do is I can take I2 and I could sub it back into D. I know I2 is 0, and so equation D, when I put the value of I2 in, will have only the unknown I1, and then we could solve for it. I don't have to put it into D. I could put it back into B, and again, once I put in the value for I2 into equation B, I1 will be the only unknown. It doesn't matter which one I sub it into, I better get the same result. Okay, so now we can sub the known value of I2 into B or D to find I1. Okay, so let's do equation B. It was minus V over R minus I1 plus 2 I2, but I2 is 0. And that has to be equal to 0. And so therefore, if you solve for I1, it's minus V over R. Let's just try equation D. And let's see what happens. We better get the same result, otherwise we have a problem. So equation D is on the right there, so it's minus V over R minus I1 minus 3 times I2, but I2 is 0. That's equal to 0, and so therefore I1 is equal to minus V over R. And so of course, these are the same. So it's nice to double check your results, because this type of problem lends itself to consistency checks. And so if you get some answers and you could calculate some results using different methods, it's nice to confirm that you get the same results using those various methods. So last thing, we got 1 minute left. Now we know 2 of our currents. We know I1 and we know I2. The easiest thing to do is to go back to the junction rule, equation A, and solve for the last unknown, which is I3. Okay, so let's sub the known values of I1 and I2 into equation A. And so equation A was I1 plus I2 is equal to I3. So I1 we know is minus V over R. I2 is 0. And so therefore I3 is equal to minus V over R. The last thing I'll say about this before I let you run away is that we got negative values for the currents I1 and I3. And so that means the current directions we happen to choose at the beginning were the wrong directions. And all we have to do is note that because I1 and I3 are negative, these currents run in the opposite direction that we chose at the start of the problem. Okay, good. So thank you very much. All of the kind of 3-branch circuits would be analyzed following exactly this procedure. And if you follow it without making errors, it will not fail you. All right, thank you very much. Yeah.
I think also some of
Yeah, I mean, for crossing the battery, the current direction doesn't matter. So it's only, are you going from the positive to the negative terminal? If you are,